Hello everyone, my name is Dr. Helen Leggett. I'm an evolutionary microbiologist at the UEA, and this basically means I'm interested in why things are the way they are, and in particular my research applies evolutionary theory to better understand the parasites that cause infectious disease. And this matters because we live in a new phase of high impact epidemics and pandemics. So of course we all know this now, but I'm not just talking about COVID-19. So in the before times, in 2019, the World Health Organization, WHO, announced that they were tracking an unprecedented 160 disease outbreaks, 9 of which were the highest grade emergency level. This means that they're transmitting freely between humans, and they have either no treatment or are resistant to treatment. And frankly, these disease emergencies are a new normal. But also at the same time, we're seeing at the same time as we're seeing these new infections, antimicrobial resistance or antibiotic resistance is ranked as the greatest threat to humanity. So it's rivaled only by nuclear war and climate change as likely to be the biggest killers of humans. And this is because antimicrobial resistance is outpacing our ability to make new cures. And these two problems of new epidemics and antimicrobial resistance are absolutely connected. So, for example, with the COVID-19 outbreak, it's sort of too early to say precisely, but current data suggests as many as 70% of hospitalised COVID-19 patients worldwide are treated with antibiotics. And this overuse will increase the long-term threat of antimicrobial resistance. But I promise this is basically the end of the heavy stuff, so I'm not here for this session to be depressing. What I really want to focus on here is the story, the history. It's our greatest medical discovery, its downfall, and what we can do about it. So before antibiotics, an alarming number of people died from simple scratches, insect bites, pneumonia, childbirth. Every hospital had sepsis wards that were called houses of horrors. Clearly, modern medicine would be impossible without antibiotics. So after antibiotics, these potentially life-threatening events of, scratches and childbirth became controllable. So everyday life is now safer because of antibiotics. So medical procedures that would have carried a lethal risk of infection are feasible and commonplace. So think about things like caesarean sections, surgery of any kind that involves bacteria-rich organs, so things like in your gut or generally your sort of body cavity, treatment that suppresses the immune system like chemotherapy for cancer, IVF or organ transplants, and anything involving catheters or implants such as heart bypass, kidney dialysis. So there's no doubt that antimicrobials and antibiotics, so antibiotics, I said before, target bacteria, and antimicrobials are like other microbes, so things like viruses and fungi. Simply no doubt that these are the wonder drugs of the 20th century. And in fact, they're responsible for extending the average age of a human life by 26 years. And we have Paul Ehrlich to thank for this, first of all. He's often overlooked in this conversation, which is pretty sad. But he developed the first antibiotic compound effective against the spirochete. So a spirochete is a spiral bacteria that causes syphilis. And in so doing, he also coined the term chemotherapy. So antimicrobial chemotherapy to be exact, and actually generally, a fun fact for you, so chemotherapy, we often think of this as being to do with cancer, but actually a chemotherapy by definition is basically the use of any drug to treat fast growing cells. And in fact, Paul Ehrlich won the Nobel Prize in medicine in 1908 for his work on chemotherapy, the immune system. You might also have heard about him for developing gram staining that we use to detect different types of bacteria. But perhaps the main guy you will have heard about is Alexander Fleming, an amazing scientist, probably my favourite for a couple of reasons that we'll come on to. He also had a local connection to Norfolk, actually, so he had a holiday home in Tuddenham, just over the Norfolk-Suffolk border. And a very long story short, that probably you've heard of, he went on holiday for 6 weeks to his holiday home, and upon his return, when he was cleaning his lab, he found that one of his sort of seminal plates was contaminated. And this is the first reason I love him. So he was an observational scientist. So probably you or I, or definitely me, I would have thought, oh my goodness, I'd left all of this rubbish before I'd gone on my holiday, and I'd have probably just binned it and killed it with fire as soon as I could when I realised that the plates were contaminated. But that's not what Fleming did. So he saw that his plate was contaminated. This is his plate in the middle of the screen here. And he saw that it had like a colony of mould on it, and surrounding that colony of mould, his Staphylococcus bacteria were dying. They'd lied. So you can see they're looking very unhealthy and very small, close to that mould at the top here. Probably you've all created penicillin by accident. If you've ever come, to make your toast in the morning and your bread looks like this, perhaps this sort of thing will happen to you when you potentially go to university. But yes, so penicillin made by mould killed bacteria was Alexander Fleming's discovery. And after him, so 2 and 10 years later respectively, we have Howard Florey and Ernest Chain, who purified penicillin, and we'll come on to this shortly. They were largely involved in bringing it to mass production, and this was only possible because in the 1940s Dorothy Hodgkin solved the chemical structure, and so we actually knew what the molecules looked like, which meant we could have an understanding of their action, how best they work, things like what pH they needed to be at to be effective, which helped in the mass production. And this really was a significant turning point in medicine. So we've already said how Fleming's discovery in 1928 and this sort of subsequent sort of mass production through the 1940s was without doubt a turning point in the history of medicine. So as I was saying before, prior to penicillin, an overwhelming number of people died of bacterial infections. And on the left here, there we can see one of these houses of horrors, so one of the sepsis wards that every hospital throughout the world had. But 10 years after Fleming's discovery, as I said, Chain and Florey were working on trying to do sort of mass production, and obviously war had broken out and was rampant throughout Europe. And actually bombings in the UK made it impossible to develop mass production. So what they did in the middle of the war, incredibly brave, was actually under cover of darkness, leave the country. They flew to the United States of America, where there was no bombing, and set up factory production with 4 drug factories, so pharmaceutical companies, including one by Charles Pfizer and Co., who Pfizer, as I'm sure you're now all aware of, have been really pivotal in making new vaccines for COVID. So we have Pfizer to thank for some of our antibacterials as well. And actually, a little known fact about antibiotics is actually just the pivotal role they played in Europe winning, or the Allied troops, should I say, the UK and the US. In winning the war. So for the D-Day landings in June 1944, all Allied troops had supplies of penicillin. So over 2 million doses of penicillin were shipped out to soldiers on the front line. And it's actually thought that the reduction in fatalities of Allied troops as a result of penicillin really was actually one of the main advantages that the Allied troops had, which contributed to winning the war. Moving on a little bit more, so sort of post-war, we're then into the work of people looking at streptomyces. So we'll be talking a bit about streptomyces. So streptomyces, bacteria, Salman Waxman was looking at them along with many other people, I should say. And effectively these types of bacteria are really important for decomposition in soils. They live in soil and make molecules or specialized metabolites that can kill bacteria, fungi, insects, all sorts of things, so that they're really, really useful. And they're incredibly useful to humans because we can use them as antibiotics, herbicides, and these anti-cancer compound. So in fact, more than half of all clinically used antibiotics are made from Streptomyces bacteria that Salman Waxman found within soil. And I love this fact. So actually I'm Norfolk born and bred. I went to school in Durham. I now live in Norwich. And Streptomyces and closely related actinomyces make 60% of all known antibiotics. And Norwich really is the home of this Streptomyces research. So the gentlemen we have along the bottom here, so David Hopwood, Mervyn Bibb, Mark Butter, and that's Matt Hutchings on the end there. These are all researchers that have or currently work on the Norwich Research Park, just near the Norfolk and Norwich Hospital. And they really are leading the way in the discovery of new types of compounds made by Streptomyces that perhaps will be some of our new antibiotics in the future. So that's really exciting. And in general, antibiotics are mostly natural products. So we've already said, so 60% of antibiotics come from the Streptomyces bacteria and their close relatives, but in general, antibiotics are mostly natural compounds made, in fact, by other microbes. And certainly if you can come to the next session, this is something that I'd like to talk about more. So we'll think about these microbial wars. Why are microbial wars so good at making antimicrobial and antibiotic compounds? And in particular, why are these so useful to us? This is something that we'll think about in that session. And really what we're talking about here, so from Fleming's discovery sort of right up till the turn of the millennium, was the golden age of discovery of antibiotics. So almost all the antibiotics in clinical use were discovered in this golden age between the 1940s and the 1960s. So 1908 there, you can see Salvarsan, which was discovered by our lovely Paul Ehrlich, followed in quick succession by all the work by the people we've been talking about. And as you can see, the majority of them are natural, so surrounded in red there. So where did it all go wrong? Well, the reality is, for the past, sort of 90 years, we've been playing a game of leapfrog with microbes. So our drugs, their resistance, and then another drug, and then their resistance again. And to be honest, the game is now ending. So in this 90 years, we've walked ourselves up to this sort of edge of disaster. And in fact, we only now have two groups of last line defence antibiotics, and resistant strains against them already exist. And it's so, I think that's sort of shown in this timeline here, so you can see just how quickly the resistance evolves against the antibiotics that were created within the labs. And in fact, sometimes even there was resistance known to an antibiotic before it was even discovered. So it really not a great situation. And it's actually sort of projected, sort of looking forward into the forecasts in over sort of the next 10 years, and with $37 billion, it's thought that perhaps 15 new antibiotic compounds can be made, 4 of which will target species of greatest concern. But the reality is that probably won't be enough. And here's why. So evolution always wins. So bacteria birth a new generation every 20 minutes, and as we've seen on the previous slide, it takes the pharmaceutical, chemistry, in excess of 10 years to drive a new antibiotic drug. And in fact, just the replication alone of some of these bacteria and microbes is completely overwhelming. And this never happens, I should say, but in reality, it would take less than 48 hours for one bacterial cell to reproduce enough to weigh the same as the entire planet. This never happens because, bacteria, they're predated, they're killed by UV, they're eaten by things, not least other viruses. But still, it's extraordinary. Just their sheer replication means that, we're always going to be playing catch up. But the other factor is, unlike any other drug used in medicine, antibiotics, the more we use them, the less effective they become to their target organisms. So with antibiotics, overuse or inappropriate use allows bacteria to develop resistance. And here we come on to our second reason of why I love Fleming. He was a visionary. So this is a quote from his Nobel Prize acceptance speech. So it's not difficult to make microbes resistant to penicillin in the laboratory by exposing them to concentrations not sufficient to kill them. The time may come when penicillin can be bought by anyone in the shops. Then there is the danger that the ignorant man may easily underdose himself and, by exposing microbes to non-lethal quantities of drug, make them resistant. So he predicted that we would have the problem of antibiotic resistance that we have now. If only we had listened. So why is it so hard to find new antibiotics? Well, antibiotics, as we said, are the product of this golden age of discovery from the 1940s to 60s, which sought naturally produced antibiotics from things like the soil streptomyces that we've talked about. But this process effectively hit the law of diminishing returns by the 1960s, with the same classes of compounds being repeatedly rediscovered and sort of few new ones emerging. So from the 1990s, scientists and researchers tried more sophisticated approaches, so genetics and engineering and synthetically trying to create antibiotics. But ultimately, this simply just hasn't been successful, and it's perhaps not surprising when you think about it, given that genetics are so specific to an individual organism, and you're effectively trying to hit a moving target, given how fast microbes can evolve. But perhaps most importantly, the problem we've had with discovering new antibiotics reflects a move by big pharma away from antibiotics, which ultimately have proved increasingly difficult to license, and which, as short-term courses of treatment, so for just like your ear infection or something, they are generally less lucrative than drugs for chronic conditions such as curing cancer. And I think here this graph this is developed from the review on antimicrobial resistance that we'll come to shortly, really nicely sums up this problem of finance. So you can see here that this is just for one sort of antibiotic compound. By the time a company brings the compound through the end of its clinical research phases at a cost of about $700 million, it takes about 23 years on average to then get profit for developing that drug. So it really, actually financially for these companies doesn't stack up to be putting research and putting money into creating new antibiotics. So that's where we have our current problem. So in these just 90 years, we've walked ourselves up to this edge of disaster where antibiotics are losing their effectiveness against infectious diseases. And the hard truth is that we don't get 90 years to find our way back out again. And in fact, it's thought we have less than 30 years. So this is a review that was published in 2016 by the British government. It was a review that was commissioned by David Cameron, not least thanks to the remarkable work of Professor Dame Sally Davies, who was Chief Medical Officer at the time. And this is sort of shown in this petal graph on the bottom left here. So in the blue, we have the current biggest causes of fatality in humans. So obviously cancer is the biggest cause of death currently, but just look at that purple petal there. So purple indicates by 2050 what is going to be the greatest cause of death in humans. And as you can see there, overwhelmingly the greatest cause is antimicrobial resistance. So we think it'll be responsible for about 20 million deaths a year come 2050. And so where we're at now is that we want to push back this date, as far as possible, anything that we can do to push back this date is what we need to be looking at now. And here on the right, we have 10 different fronts of tackling this problem, and we'll think about these in the next session, and in particular the ones that I've highlighted in red there. So things like public awareness, sanitation and hygiene, vaccines and alternatives, and antibiotics in agriculture and the environment. These are the ones that I'd particularly like to focus on. So in other words, I hope you can see that, this is highlighting that, just how much of an interdisciplinary problem we're facing here. So in other words, it's not just a biology and chemistry problem, it's a political problem, an economic problem, social and ethical problem too. So what can we all do about it right now? So that's what we'll talk about and discuss next time. And so ahead of that, focusing on these four topics for tackling antimicrobials that I've highlighted in red, perhaps some things that you can think about how you would answer these questions. So antibiotics, they're a shared limited resource. So how do our individual personal ethics affect the problem of antimicrobial resistance? Also think about how does environmental antibiotic pollution affect antibiotic resistance. So in particular, I'm sort of thinking of livestock farming, for example. And also, as I said at the start, I'm an evolutionary biologist. So I love thinking about how plants and animals evolved in a world smothered in microbes, which is what we have on the left there. So what are the consequences of this? So it might help to think about which natural compounds we can screen, why they exist. So this is what I was saying about earlier in my previous question. So, why have microbials become so good at winning microbial wars? So think about the world in which microbes and, we, humans, plants, animals, evolved. And that might help you then think about where we should look for new antimicrobials, and also what the consequences are. So we're messing with our symbioses, so our relationships with microbes. We're interfering with them all the time, not just by using medicine, but also sanitization and hygiene. So perhaps have a think about that. Think about whether you think all microbes are bad. And in general, then we do have some bad ones, but why do these microbes, why do some bacteria cause us harm? So when you think about it, that might be a little bit counterintuitive as well. So thank you very much. I hope you enjoyed that, and hopefully I'll see as many of you as possible at our next session where we will answer some of these questions. Thank you.